Alright guys, welcome to Chapter 7. Chapter 7 we are looking at ratios and proportions. And we'll kind of explain the difference between those two, but let's just start with ratios. The first page that we're going to go through is really just a focus on ratios, and then the second side of this page is going to focus on proportions. So a ratio, as it says right here, is simply a comparison of two things. Right? So if I want to compare one thing to another thing, then that's a ratio. So there's a couple different ways we can look at this. When you write it as a fraction, so if I'm going to compare A to B, right, we can write it this way as a fraction. And remember that fractions are division. So this is like saying A divided by B, or you could say A out of B, right, if we want to look at it that way, because this usually represents a total, and that usually represents part of that total. The other way to write it is this way. So we can also go side to side with a colon in between the two quantities and compare them that way. So just remember that anytime we're comparing two things, that's what's called a ratio. So we're going to go through just a handful of examples here so we can see how some of this is going to get set up. So in the first example, they're talking about the Red Sox who won 96 games out of 162 games. So kind of a key phrase that we're seeing right here, right, out of. So what they want us to do is simply write the ratio that compares how many games they won to the total number of games that they played, right? So they won 96 out of 162 games. So here's one way of writing that, is we can say they won 96 out of 162 games. So again, they are comparing the games won to the total number of games they played. This is the comparison that we're seeing, right? Another way you could write this, as we saw up above, would be to write it as 96 compared to 162. All right, so that's the other way that we can write this. This is probably the most common way of writing a ratio, is with a fraction, but this is just another way of writing it. Still means the same thing. These numbers can be reduced, so they can be simplified. Oftentimes, especially when it comes to sports, we usually see these things as a percent, right? We might say, what percent of the games did the Red Sox win that year? Well, remember, this is just division, right? So if I go into my calculator and I did 96 divided by 162, then I can see this now as a percent. So they won about 59% of their games, if we round that off. All right, so let me move it on down to this guy for example 2. So with example 2, usually what you're going to see on this problem is only what you see right here in bold, right? This stuff is part of the work that we would put into figuring out how to do this problem. But this is a really common ratio problem for geometry. So I'm sure we're going to run into this one a few times along this chapter. What they're saying is that the ratio of the angles of a triangle are 2 to 3 to 4. So one thing to keep in mind is those are just how the angles compare to each other. They're not actually their values, right? It's not like 2 degrees, 3 degrees, 4 degrees. It's just telling you how they relate to each other. So for example, when I look at these numbers, I can see that whatever angle this is referring to is twice the size of this angle, right? So all we're really seeing on this is how they compare to each other. Our job is to figure out what the real numbers are. So what they're going to do on this is they're going to say, well, let's keep in mind that the three angles of a triangle add to 180, right? We've been through that many times with previous chapters, so we know that's a rule that is true. So the way we can identify some real values for this is to say, well, I don't know what the real numbers are with this ratio, but let's put in the x's that shows the comparison. So this is 2 times something, this would be 3 times something, and this would be 4 times something, right? And so here it is within the diagram. So I got 2 times some value, 3 times some value, and 4 times some value is going to give us the angles of that triangle right there. So now we can kind of connect those with our triangle sum theorem and say that we know they're going to add to 180. And then if we go through the algebra on this, we figure out that x is 20. So if x is 20, what would that make each angle? Well, we know that 3 times 20 would give us 60. We know that 2 times 20 would give us 40. And we know that 4 times 20 would give us 80. Right? And so now we can see the comparison with the real numbers now that we figured it out. And you'll notice all 3 of those add to 180 if we add those up. You're also seeing what we talked about before. Remember how I said that I could tell that this guy, when I compare it to this one, is only half. Right? I can tell that because this is 4x and this is 2x. I know that 4 is twice the size of 2. So when I look at the real numbers, I can see how that played out, right? 80 is twice the size of 40 when I look at the real numbers. So I want to go down and just run through a handful of these examples with you that I put in, just so you can get plenty of practice in setting these up. So here's one similar to that first one that we did. And guys, always at any time, you're welcome to pause the video, try these ahead of me, and then play the video and see if you got them right. So in this one, they're talking about A-Rod hitting 54 home runs out of the 583 times he came to the plate that season. So what is the ratio of home runs to the number of times he was at bat? So home runs, and guys, you do want to put these in the order that we read it. So when it says a ratio of home runs to the number of times he was at bat, that's the order that I need to write this in. Okay, because they could flip that around and then I would have to flip my fraction around to match it. So the order on this does matter. So home runs, well, he hit 54 home runs. Compared to how many times was he at bat? Well, he went to bat 583 times. So pretty impressive, right? So there's the ratio of home runs to number of at-bats. Just like any fraction, do keep in mind that if this is reducible, you can reduce it. There's nothing wrong with that. There's plenty of things we can do with a fraction once we write it. We could convert it to a percent, just like we did up above. So if we wanted to say what percent of the times did Alex Rodriguez come to bat and hit a home run? So 54 home runs out of a total of 583 at-bats. So you can see a little over, if I move my decimal 2 places, then a little over 9% of the time he was hitting a home run when he came to bat, which is just amazing for baseball. So a lot of different ways we could look at these numbers. So let's move on to this guy down here. So there's 182 girls in the sophomore class out of 305 students. So there's 305 students that are sophomores, and of those 305, 182 of them are girls. So what ratio of girls to total students? Real similar to the one we just did up above. Girls to students. So 182 girls compared to 305 students. Right, so there's a great way of writing it. Again, we can say, we could write it this way and say 182 compared to 305. So we can write it with a colon instead. Nothing wrong with that. But like I said earlier, this is just the more common way of looking at it. Let me just throw in a little bonus question here for you. What would be the ratio of boys out of the sophomore class? So if there's 305 kids and 182 of them are girls, how many are boys? So if I did 305 minus the 182 girls, well, I can see that there is 123 boys within the sophomore class. So that's a question they could easily ask from the same information, right? And maybe I would have to do a little subtraction and say, well, as far as boys to the total, there's 123 boys out of the 305 students. They could also ask you something like, what's the ratio of girls to boys? Well, if we said girls to boys, we already know there's 182 girls compared to 123 boys. So there's now the ratio of girls to boys. One of the things that's really helpful as you go through word problems especially is labeling. If they ever ask you multiple questions, really helpful to label what you have. Like if this represents girls and this represents boys, it will help you to label things if you're going to use that same information for future processes. All right, let's go on to the next one. So length of a rectangle is 8 inches and its width is 5 inches. What is the ratio of length to width? So remember when I said earlier that the order matters on this? The order matters. So if they're going to say length first and then width second, I want to write my answer the same way, right? So if my length is 8 compared to a width of 5, then I want to make sure that I write my answer in the order that it reads within the problem. That's important. I don't want to switch those around. So you can write it again that way. Of course, we could have said 8 to 5. And it does help to label. So if I were to say this is my length and this is my width, labeling is always a good thing too. All right, let's go on down to the last two on this page. So the ratio of the sides of a triangle, So keep in mind, these are not angles. These are sides, unlike the one that we did up above. So this one's just a little different. Perimeter is 480. Let's see if we can figure out the length of each side. So two things that kind of go into setting this up. One is to recognize that these are ratios, right? These are not lengths. These are simply how the lengths compare to each other, right? So we don't know what the actual lengths are. I just know this is how they relate to each other. So in other words, I could say something along the lines of whatever this one is, it is almost double the length of the shortest side. We don't know what the lengths are, but I do need to understand that's how they relate to each other. Okay, so I know this is 8 times something. I know this is 15 times something. And I know this is 17 times something. So the way that we can set up an equation for something like this is to use this second piece of information that tells us something about the sides of this triangle. Well, the perimeter is 480. Well, how do you ever find a perimeter? We add up all the sides, right? So that's what a perimeter is. It's when you add up all the sides of anything, then you have its perimeter. So if I simply add those three sides together, I know that they total 480 because that's my perimeter. So there's the equation that we have now set up, and I simply need to do the algebra to solve for x. I'll go through it real quick. So let's see, if we add these together, that would be 23 plus 17 would be 40x is 480. And then if I finish this off by dividing both sides by 40, let's see, it would go in 12 times, I believe. So x is 12. One of the things we always want to be careful of with word problems is making sure that we answer the question. It didn't say solve for x. It said find the length of each side. So I now need to plug this back in to get my side lengths. So in other words, I would have to do 8 times 12 to get that side, 15 times 12 to get that side, and then 17 times 12 to get the third side. All right, so that would be the final step that you would need to do to finish off this problem. And that's just calculator work, so I'll let you guys, I know you guys could do that one on your own. So here's one that you could try on your own if you want to pause and give this one a shot. This one is going to be a little more similar to the example that I did up above, right? Because this now represents the 3 angles of a triangle, whereas this one represented sides of a triangle. So a little different when we look at these as far as how we're going to set up an equation. Again, we just know the comparison of these guys. So 7 to 9 to 20. So I know that 7 times something is going to represent the small angle. I know that 9 times something, that same value, would represent the middle angle, and then 20 times something is going to represent that third angle. And now with this one, we have to remember that because these are angles of a triangle, I know they add to 180. So after you're putting in those x's, the main goal on those is to figure out how do I relate them in an equation, right? If they're angles, then they relate by adding to 180. You know, if they were sides of a triangle, they relate by adding to the perimeter, right? So this setup can change depending on what information is given right here. Okay, so for this one, we understand they add to 180 because they're angles of a triangle. And again, just do the algebra to finish them off. So what do we got? 16 plus 20 makes it 36 equals 180. And if I divide both sides by 36, then we'll get our value for x. Let's see, what's 180 divided by 36? Is that 6 times? I guess it would be 5 times. So if I divide both sides by 36, I figure out that x is 5. And again, I'm not done yet, so keep that in mind. We need the measure of each angle. So again, I have to plug this back in. So if I did 7 times 5, I know my smallest angle is 35 degrees. If I did 9 times 5, I know the next one is 45 degrees. And if I did 20 times 5, I know my biggest angle is 100 degrees. Right? And of course, if you add those together, you can check them. They do add to 180, so we know we're on the right track here. Okay, let me get past ratios and move into proportions for part 2. Proportions are simply a comparison of two ratios. So remember, a ratio is like a fraction, right? Well, when I relate two fractions, I now have a proportion. So a proportion is simply when you have multiple ratios, right? So this ratio equals this ratio, and that makes this a proportion. All right, so one of the things that you would have learned back in your pre-algebra days is something called cross-multiplying. So when I have a proportion like this, we can do something called cross-multiplying. Here's sort of the general outline of that, right? In other words, we are doing A times D is equal to B times C. I've had a lot of students tell me in the past that they've had teachers that call this like the butterfly or something like that, because their teacher would do something like this. So it kind of looks like a butterfly. So I know that A times D is equal to B times C, right? And so they call this the butterfly method, or cross-multiplying, cross products, whatever you want to call it. It's a pretty simple process, and it's one that I know you guys have seen before. So let's just walk through this example they already laid out for us. So when I have a proportion like this, again, I know that 9 times x is equal to 16 times 27. And so here's the setup that they got from doing that. And then from there, it's going to be very basic algebra to get x by itself. I want to show you guys a little shortcut, because this is one that I use personally a lot. And I think it often gets overlooked. If I go back to this proportion, and I want to look at, remember, this is an equal sign. This fraction is equal to this fraction. So when I look at how did they go from 9 to 27, well, whatever they did has to be the same thing as how they went from 16 to whatever this is, right? So as I just look across the top, I can look at this and say, well, how did they go from 9 to 27? Well, they multiplied times 3. And whatever they did to the top, you would also have to do to the bottom. So if I did 16 times 3, I get my answer right here, which is 48. And so that's another way of getting that missing piece of the puzzle up there. So it's a method I prefer, to be honest, but cross-multiplying is a great way to go. Here's the one downside of this is, what if this was a number like 26? Right? Well, I don't know what you would multiply times 9 to get 26, because it's a decimal. Right? So if it doesn't go in evenly, then this rule kind of breaks down and it's not so great. And that's when cross-multiplying is the best way to go. But if it does go in evenly, I think this can be a shorter way of doing it. Let's take a look at a little word problem here. All right, so we got a mayor that conducted a survey of 200 voters, found that 135 of them approve of the job she's doing. So remember how we look at a fraction or a ratio, is it's best to say something out of the total, right? So we generally like to put the total on bottom, and we like to put part of that total on top. In fact, you probably had a teacher somewhere in the past that referred to fractions as part out of the whole. They would say whatever you have on top is part of something, and whatever you have on bottom is the whole thing, right? So you might have seen that before. So my total is 200 voters, and part of those voters, 135 of them, approve of the job she's doing. So you can see the setup that gave right here. So 135 out of the total of 200. And then we're going to compare that to another ratio on the other side so that this becomes a proportion. So it says there was 48,000 voters in the town. Remember, that's a total. There was a total of 48,000 voters. So I know that's something that I want to put on bottom, because whenever I get a total or a whole number like that, right, it represents all the voters in the town. I know that goes on bottom. So how many voters out of the total would approve? Well, we don't know what that is, so that's what we're trying to solve for. So this is part out of the whole, and now we have a proportion. We just do a little cross multiplying to get our solution. We're going to do some together. I just wanted to give you a little exposure to a word problem, and we're going to do a little more of that when we get to the bottom of this. All right, so let's do a little for practice here. Okay, so let's do some cross multiplying. So as I look at number 1 here, again, we're going to do the butterfly method or the cross multiplication. So I know that 1 times x, so 1x, which is just x, you really don't need the 1, equals 2 times 28. So if I simplify that, 1x is just x, and 2 times 28 is 56. And we have our answer for x. And guys, notice, remember, this fraction is equal to this fraction. So this is 1/2, 1 out of 2. Well, 28 out of 56 is also 1/2, right? 28 is half of 56. So we want to make sure that relationship is looking good. Let's do the same thing on this one. Again, you can always pause and try this ahead of me. I want to try the shortcut on this one. So if I wanted to try something I mentioned up above, one thing I could do is say, well, how did they go from 8 to 24? Well, they would have to multiply by 3, right? Well, whatever they did on bottom, you would also have to do on top. So what's 3 times 3? Tells me y is 9. So, guys, either method is good, right? Whether you like doing it this way when it's available, or you're good with the cross multiplying, we can take either path. They should both give us the same answer. All right, let's try one more here. Here's kind of one where you really need to do the cross multiplying, right? This is not the best way to go in all cases, right? It's only kind of some basic cases that was kind of the best way to go. Here's something you can do if you want. You don't have to. 30 over 10. Can we reduce that? Absolutely, right? So if I wanted to, I can reduce 30 over 10 to just become 3 over 1. And then cross multiply, right? And maybe you would prefer doing that because then you get to deal with much smaller numbers. So that's what I would do personally in a case like this. I'm going to do that in a second. I'm actually going to do it both ways. I'll go through it real quick. So let's just go very basic cross multiply. So I'm going to do x plus 22 times 10. So 10 times x plus 22. And on the other side of my equal sign, I got these guys. So 30 times x plus 2. So there's our setup. and we're just going to go through solving this simple algebra problem. Guys, this is super, super important. I hope you're noticing this. The 10 and the 30 need to get distributed, right? I don't want to multiply the 10 over to here and just call it 10x plus 22, right? I'm not going to get the right answer if I go that route. I'm multiplying this 10 times everything that I see up here, not just the x. So I want to make sure that it gets distributed. So when you write these out, make sure that you write them with parentheses, just like we did in this one. So that way you remember to distribute. So I'm going to distribute my 10. And on this side, we'll distribute our 30. Subtract 10x from both sides. And let's subtract that 60. And then if I divide both sides by 20, I should get x is 8. All right. So guys, again, what you could have done on this, if you want, is you could have said, I'd much rather deal with smaller numbers. Why not reduce? So instead of using 30 over 10, I could have used 3 over 1, right? Because it's the same thing. 30 over 10 is the same thing as 3 over 1. So even now, if I would have used these smaller numbers, now if you cross multiply, you will still get the same answer, but it's smaller numbers, so maybe that would be a little friendlier if you want to go that route. All right, peek at these last two with me and then we'll be done. So if 3 DVDs cost $44.85, what would it cost to buy 1 DVD? Well, I got 3 DVDs, and I know they cost $44.85. So here's something you're going to hear me say about 1,000 times throughout this chapter. When you're writing a proportion, the thing that is super important is however you set up the left side, you got to set up the right side the same way, right? So if my top represents DVDs and the bottom represents dollars, I got to do the same thing over here, right? That has to represent DVDs and that has to represent dollars. So we got to make sure that we're being consistent with both sides of our proportion here. So what's the cost? So that's what we don't know, is we don't know the cost if I have 1 DVD. So there's our setup. And again, guys, you could now cross multiply, just like we did on the previous ones, and you could solve for x from there. Let me set up one more word problem with you. So Byron's measuring plants in a field for a science project. On the first 25 plants that he measures, 15 of them, so remember you have a total of 25 plants, and out of that total you have 15 of them that are smaller than a foot in height. So 15 out of the 25 are smaller than a foot. If there are 4,000 plants in the field, so again, this is a total, right? There's a total now of 4,000 plants in the field. I know I like to put my totals on bottom. 4,000 plants in the field. So how many of that total are smaller than a foot? So remember the 15, the number on top, was what represented the number of plants that are smaller than a foot. And that's what we're trying to figure out if we had a total of 4,000. So again, guys, from here you could just simply cross multiply. Remember, there are some shortcuts to this. So for example, if you would rather work with smaller numbers, you could reduce that fraction first and then cross multiply, right? Totally fair game if you want to do that first, but yeah, so I wanted to set up this one more word problem with you. The cross multiplying is just going to be identical to all these examples that we did up above, so we're going to call it good for this one.